I'm excited to share our work, Mismatched, No More, Joint Model Policy Optimization for Model-Based Reinforcement Learning. Model-based reinforcement learning is exciting because of what it promises. If you could learn an accurate model of the world, you could use that model to solve any tasks. For example, if you could learn this model of a driving scenario here, you could learn how to navigate the roads of the world. But learning an accurate model is hard. Turns out that, say, predicting where bikes are going to go on the road is really, really challenging. And ultimately, all of our models are going to be wrong, and we have to figure out what to do about it. The aim of this project is to figure out how to learn and use models that can produce good policies, even when the model might be inaccurate. Model-based RL methods typically have two components, a model and a policy. The model generates experience that is fed to the policy. The model is usually updated to be as accurate as possible, and the policy is updated to achieve high returns. These two objectives are different. Ideally, making the model more accurate would make the policy get higher and higher returns. But this is usually what happens, where at some point the model becomes more and more accurate, but the policy actually starts achieving lower returns. And the reason for this is that the inputs to the model are not IID, but they depend on the states that the policy visits. And as we update the policy will visit different states. It makes sense it might end up visiting states where the model makes more mistakes. The difference between the model objective and the policy objective is sometimes referred to as the objective mismatch problem. And there's been a lot of really interesting work trying to combat this problem, usually by changing how the model is trained. The key idea in our work is that we can also change how the policy is trained so that the policy visits states where the model is accurate. We'll propose a method where we jointly optimize the model and the policy using the same objective. And this means that updating the model will make the policy achieve higher returns, and updating the policy will make the model more accurate. Thus, we'll end up learning a model and a policy that are jointly trained to be self-consistent, thus resolving this objective mismatch problem. Here's the main idea behind our method, which builds upon prior work. The reinforcement learning objective is the sum of rewards, and it can also be written as this integral over trajectories, where you look at the probability of each trajectory multiplied by the rewards along that trajectory. Now, these trajectories can be viewed as unobserved random variables. We don't know what states and actions they correspond to, but we want them to achieve high rewards. Let's look at an example. On this navigation task on the right, we want the agent to navigate from the start around the obstacles to the high reward state. What might these trajectories look like? They might look like something like this. These trajectories, they correspond to both states and actions. So if we could learn these trajectories, we would have learned both the model and the policy. Now, thinking about reinforcement learning as this latent variable problem, it suggests how we should learn these trajectories. We can infer them in the same way that we infer latent variables for other problems, like a VAE. Here's how we do that. We maximize an evidence lower bound on the reinforcement learning objective. It consists of two terms. The first term says we want to maximize rewards, and the second term says we want to produce trajectories that are similar to the real environment dynamics. One thing to emphasize about this bound is that it's jointly optimized with respect to both the model and the policy. Also, there's an expectation with respect to the learned dynamics, which means we can estimate and optimize this bound without requiring more data from the environment. The second term here requires looking at the difference between the learned dynamics and the environment dynamics. And we can estimate this term by learning a classifier, just like a GAN. On benchmark tasks, our method performs roughly on par with prior methods. And this is really good because it means that achieving theoretical guarantees doesn't necessarily cost us in performance. And on certain hard exploration tasks, we can significantly outperform prior methods. One thing I want to highlight about our method are the ways in which it goes against the grain. Most obviously, our method optimizes one objective, whereas prior methods optimize two. These two objectives are often viewed as competing, whereas our method cooperatively optimizes the same objective. More interesting is the fact that our policy is optimized to make the model more accurate, and also that the model is optimized to help the policy explore and achieve high rewards. I think this is interesting because it suggests a pretty different reason for considering model-based reinforcement learning at all, not to improve data efficiency, but rather because it might be beneficial for exploration. So to conclude, this project is about jointly optimizing models and policies with the same objective. This is potentially useful because it simplifies the algorithms and also strengthens them by giving them new theoretical guarantees. Broadly, I think this latent variable perspective is neat because it offers guidance on how to convert powerful generative models into reinforcement learning algorithms. Please stop by the poster to learn more about more experiments and future directions. Thanks.